YouTube channel Raise a Cat. Myself Yash Mishra, and today in the thermodynamics part we will see one more question on the turbojet. So in this the some values are given and the terms we have to determine. So let's see what is the question and what are the values we have to determine in this question.
In this question there is a turbojet which is flying with a velocity of 275 meter per second and at an altitude of 6100 meter. Okay, and the ambient conditions are given as, or the outside pressure is given as 50 kilopascal and the temperature is minus 12 degree Celsius. So these are the conditions which are given, and the pressure ratio across the compressor is 13. Okay, and the temperature at the turbine inlet is given as 1330 Kelvin, and we have to determine the pressure at the turbine exit, velocity at the velocity of the exhaust gases, and the propulsive efficiency. So these are the three things which we have to determine, and this is the data which is given for the question. Okay, so these are the assumptions which we have to keep in mind. There is a steady operating condition exists. Air standard assumption is applicable. Air is ideal gas with constant specific heat. Kinetic and potential energy are negligible. Turbine work output is equal to the compressor work input. So these are the assumptions which we have to keep in mind while solving the question. Okay, and these were the values which are given to solve the question, and these are the things which are asked to determine. Okay, so moving further, and these are the Cp values and the K values. As it is not a simple process, this is a polytropic process. For the polytropic process, the equation is PV to the power of n is equals to constant. So in adiabatic process, n is gamma. In some other process, it is like that. So pressure is constant. V is so it is like that. PV is equals to constant. V is directly proportional to 1 by V in case of isothermal process. Okay. So this is the equation for the polytropic process, and this is the diagram for this process, T versus S diagram, and these are the pathways which is being followed. From the 3 to 4 the energy is being given, or the Q is going in, and from the 6 to 1 the energy is going out. So it is being divided in the 6 steps. Okay, and writing the energy balance for this equation, E in minus E out is equal to delta E system. Since there is no energy change, so delta is equals to 0. So E in is equals to E out, or HI plus VI square by 2 is equals to H2 plus V2 square by 2. HI and H2 are the potential energy. VI and V2 terms are the kinetic energy of the system. Potential energy plus kinetic energy initial is equals to potential energy plus kinetic energy final of the system. This which we have done in this question. Okay, in the energy balance. So solving it further, 0 is equals to H2 minus H1 plus V2 square minus V1 square by 2. It can also be written as Cp T2 minus T1, this term, minus V1 square by 2. So the T2 value is equal to T1 plus V1 square by 2 Cp. Putting the values, we will get the value of T2 as 298.6 Kelvin. So this was the approach from energy balance we followed, and from here we changed the energy to Cp T2 minus T1 and solved this value and got the temperature value T2 as 298.6 Kelvin. Okay, so we know in the polytropic process P2 is equals to P1 T2 by T1 to the power of n upon n minus 1. So here n is k upon k minus 1. So here the k value is given as 1.4. Putting the values, we got the pressure P2 value. Temperature T2 we already got. We can easily get the value of pressure P2. Okay, so for the polytropic process we have to know what is the pressure relation. P2 is equals to P1 T2 by T1 to the power of k upon k minus 1. This is the relation for a polytropic process. Okay, so in the adiabatic process, what will be the relation? P2 is equals to P1 T2 by T1 gamma upon gamma minus 1. So this was the relation for the adiabatic process. So for the polytropic process, in place of gamma it will be replaced by the value of k. Okay, so moving further, for writing for the compressor, so P3 will be equal to P4 is equals to gamma P into P2. Okay, so putting the putting the values, we got the pressure P3, okay, and the temperature T3 is equals to T2 into P3 by P2 to the power of K minus 1 upon K. Using this polytropic process equation for finding this temperature T3, we will put the values of T2, P3, P2 and value of K. We will get the temperature T3. So we got temperature T3 and pressure P3 for the compressor, okay. So this was the approach which we followed to find these two values, okay. So moving further and finding this, for writing this equation for the turbine, W for the compression inlet is equals to work done for the turbine outlet, okay. So H3, so it will be equal to the H3 minus H2 is equals to H4 minus H5, or Cp T3 minus T2 is equals to Cp T4 minus T5. It is just an energy balance, okay. So T5 will be equal to T4 minus T3 plus T2. We will solve and we can easily get the value. What will be the value of the T5? Okay, so P3, T3, T5 and P2 and T2 values. These are the 5-6 values which we got from the values which were given in the question. Okay, so just an energy balance we are using. So finding this pressure P5 will be nothing else but P4, T5 by T4, K minus 1 by K minus 1. So this is the standard equation for the polytropic process which we have to remember. And if we have to change anything in this P5, P4, T5, T4, we can write this PV. You can use PV is equals to nRT. Suppose that we have to introduce V in place of this T5. So what we will do? We will simply replace T5 with PV. Okay, PV to the power of K upon K minus 1 upon T4 in place of T4. We will write P4 V4 to the power of K upon K minus 1. Okay, and we will solve and separate this P and V and get the relation between P and V. So if P and T relation we remember, so P and V relation we can easily get. Okay, so writing the equation for this nozzle for the aircraft, so T6 is equals to T5, P6 by P5 to the power of K upon K minus 1. So just this PV T relation we know, then we found the relation of TP. So we don't have to remember every relation. One relation if we remember, we can find the PV relation, we can find TP relation, we can find VP and PV. So these 6 relation we can easily determine if we can remember the one relation of P, or any relation if we remember, we can just replace it by the equation of the ideal gas. PV is equals to nRT. Suppose that we have to replace T, so replace it by PV. We have to replace, if suppose that P, we can replace it by T by V. So like this we can replace every value which are given in the question. So performing next the energy balance. So from here the T6 value we will know and the P5 value we already know. So writing this energy balance, E in minus E out is equals to delta E system for the nozzle. Okay, so H5 plus V3 square by 2 is equals to H6 plus V6 square by 2. So 0 is equals to H6 minus H5 plus V6 square minus V5 square by 2. So this was the energy equation which we wrote for the nozzle. Just an energy balance, potential energy plus kinetic energy initial is equals to potential energy plus kinetic energy final. Okay, and the values were given for the question, and we replaced H6 minus H5 with Cp T6 minus T5. Okay, and we can easily get the value of V6 which is given, because the T6 and T5 we have already found from the values which were given in the question. Okay, so moving further for finding this propulsive efficiency. So propulsive efficiency is defined as the ratio of propulsive work upon the heat input which is there. So this formula we have to remember, the ratio, the propulsive efficiency is defined as propulsive work upon the heat input. Okay, so WP is equal to V exit, velocity at exit, minus velocity of inlet into velocity of air. So WP is defined like that. Putting the values, we can easily get the value of WP which is there. Okay, so So here the value of Q in will be equal to H5 minus H4, which will be further equal to, like for previously we solved, T5 minus T4 into Cp. Okay, so putting the value of Cp as 1.005 and T5 and T4 values, and we get the value of Q in, and the neta P, or the efficiency, propulsive efficiency formula we have to remember, which is equal to Wp upon Q in, work done upon heat input. Okay, so we will put the values of Wp and the Q in, and we will get the propulsive efficiency. Okay, propulsive efficiency was the propulsive work, which is Wp, and the heat input. Okay, so we will put the values, and how we will find the propulsive work, which is equal to the difference in the velocity into the velocity of air. Okay, so like this we found the propulsive work, and v square by 2. Okay, so and we found the what is the propulsive efficiency, which is equal to the propulsive work upon the heat input. Okay, and the heat input is equal to the Cp into change in temperature T5 minus T4. Cp value we know, and T5 and T4 we found previously. We will put the values and get the propulsive efficiency which is required. Okay, thank you.